I want to discuss regarding the simulation. So how we can simulate this kind of a structure, how we can simulate the silicon photonic waveguide, silicon photonic modulator, silicon laser, how we can do this kind of application. So to model the waveguide coupling, rack coupling, or ring resonator, phase control, we have some tools that we need tools actually to simulate this kind of a structure. So there is a solution. The Ansys give a complete photonic design ecosystem. So Ansys work in different level, in component level and in circuit level. So in the component level, Ansys give a numerical mode, numerical FDDT, and multiphysics. These kind of packages simulate the photonics in a component level. So, and there is a compact model library that Ansys proposed that we can use the output of this component and study the fabrication deviation, study the fabrication rules, and do some statistical analysis, mode-call analysis. And the output of this package goes to the circuit, and you can create your circuit like electronic. In electronic, we have a BJT, for instance, we have IC, we have some different input and output. We can create a circuit, and then we analyze our system, our circuit. So here also is similar. We have a different component. We want to in a numerical interconnect, we connect this kind of component together and create a circuit, and the output of circuit, for instance, go to the optical spectrum analyzer, to go to the oscilloscope, eye diagram. We can analyze, see the frequency domain and time domain, and it's very helpful. It's very helpful in design. So it helps for the designer what's going on their design. So, but not only you don't need to. You are not limited to use just Ansys part. You know, Ansys gives you other options, like, for instance, instead of the component, use the component simulation that you can use by Ansys numerical FDDT mode or multiphysics. You can use your experimental data and import the experimental data to the numerical interconnect, and also you can do some simulation with the in the component level with Ansys software, and the output of the component can goes to the, for instance, Virtuoso or Photonic Verilog A. So this is some example that, for instance, when we want to simulate a waveguide, like based on FDE solver. You know, based on FDE solver, we can create we can calculate a group index, dispersion, coupling length, overlap, and this kind of application. So let me show you one example of the waveguide with, okay, so this is the general view of numerical mode. And as you see here, for instance, in the waveguide design, we have a substrate, we have a clad, and we have a waveguide. This is our waveguide, as you can see here in this picture. And the material of our waveguide is silicon, as you can see here in this picture. And the height of our waveguide is 220 nanometer. So easily, this is actually a general view of numerical mode. You can define your material here. You can define your structure. And so let's start to simulate this waveguide. And this is output of, you can see the mode is confined to the waveguide. We can see a different modes here. Now I want to calculate the group index, dispersion, or other parameters of the numerical mode. So we can go to the frequency analysis and then do some frequency sweep. So you can see here the effective index versus wavelength is calculated. So we can see different parameter like effective index, loss, gain, group index, group velocity, dispersion. For instance, this is the dispersion. And we can export this file to a different format, like as we want, as we wish, to MATLAB text file. Yeah, this is one example. So another example is tapered waveguide. So the workflow of tapered waveguide is that, so we can use a numerical mode to optimize the waveguide taper geometry, and then we can extract the S parameters, the compact model library, and import it to the numerical interconnect. So let me show you how it works. So this is an example of numerical mode, but not similar to the previous one. This is eigenmode expansion method. Because your geometry changes along this direction, so we need use a EME solver. So so this is a input. This is our left waveguide. This is input, and this is output, and this is our polygon that we want to generate a taper. We optimize this slope with the numerical mode, with the numerical script, with the numerical Python. For instance, with Python script, you can optimize this structure. So, for instance, this is the input of the tapered waveguide, as you can see here, and this is the output. Just as an example, I want to show as an example. Yeah, and you can see mode profile along the x-axis. Yeah, as we can see, mode when goes to the x-axis, we see that the mode is spreading along the y-axis. So you can write the script. There is some script in like this mode. This is a script window that you can write the code. And for instance, we can say that, okay, calculate the S parameters, and then we can save the S parameters to the file, and then we can go to the numerical interconnect here. This is a numerical interconnect. You know, we use our waveguide here. Just I need to load the file from the place that I generate S parameter. So here I generate the S parameter, as you can see here. This is a waveguide, and we want to analyze that. So how we can analyze this waveguide? So we can connect it to the optical network analyzer. So as we can see here, we connected to the optical network analyzer, and now we want to see the output. Visualize. Yes, we can see that the different wavelengths we have, we can see a transmission in different wavelengths. But in the numerical interconnect, you access to different analyzer. You can see digital analyzer, electrical analyzer, optical analyzer. For instance, in the electrical analyzer, you can access to eye diagram, oscilloscope, power meter, a spectrum analyzer. For the optical one, we can see a optical power meter, optical spectrum analyzer, and for the sequence generator, pulse generator, we can see that for the pulse generator we have different source and modulator, passive devices, spirometer. I mean, you can also use a current library of the numerical interconnect, but you can use our model. It depends the design. So it's very simple. Now in the next step, so the workflow of we see the workflow of paper waveguide here. So as you can see in the numerical interconnect, we have a different model, different waveguide, grating coupler, directional coupler, different modulator, photodetector. We have a frequency and domain analysis. We can access to the time domain analysis. So it's good. And also we can use a Python in photonic component design. For instance, imagine that we have a Y branch and we want to optimize the Y branch, as you can see here in this picture. Optimize what is the base shape for the Y branch? So with the numerical FDDT and Python, you can optimize the Y branch. So as I mentioned before, when we want to couple the light from the free space, from the fiber to the silicon waveguide, so it's difficult because the diameter of fiber is around 9 micrometer, and the height of our waveguide is around 220 nanometer. So to couple the light from the fiber to the waveguide is difficult. So we have two strategy: edge coupling and grating coupling. So this is one example. For instance, this is one example that this is a silicon waveguide, as you can see here in this picture, and silicon nitride. We have some layer of silicon nitride, and this is one example for the edge coupling, and yeah, it's very simple again for the edge coupling. Yeah, the structure that I've showed you in my PowerPoint, you can see here, this is the silicon layer. This is a silicon nitride, different layer of silicon nitride, and we can see we can put different monitors here and see what's going on the mode behavior. For instance, here you can see here, this is a spreading of mode in the early of the waveguide, and as we go through the waveguide direction, we can see that a nice confinement. So this is one example of edge coupler. And also you can see in the numerical interconnect what's going on in the efficiency and how it works in the efficiency. If we connect this edge coupler, I mean, imagine that we have a fiber and then the fiber coupled the um, the photonic chip that I showed you. So if we go to the transmission and visualize the transmission, we can see for instance, for 1.55 micrometer, the coupling efficiency around 0.92. We can optimize it. We can work on it. We can simulate our structure. It's just one example. So we have also edge coupling is one of the solution. You can use a grating coupler. So in terms of which coupler is better, edge coupler is better or grating coupler is better. So for instance, the schematic that I've showed for my case, for my photonic chip case, I've used a edge coupling because of the bandwidth, because we need a huge bandwidth. But sometimes you don't need a lot of bandwidth. It's a small bandwidth is enough. So in that case, you can use a grating coupler. So this is example of grating coupler. So let me play the movie. You can see the light coupled from the fiber to the grating coupler, and we see a nice confinement to the silicon photonic chip, waveguides. So up to now, we talked about the passive devices. Now we need sometimes active devices, like we want to simulate modulator, we need to simulate laser. And so in that case, we need a charge solver. So the charge solver actually solves the Poisson continuity and drift diffusion equation, supports electrical contract, doping, bulk, semiconductor, and supports 3,5 material, silicon material. And also there is another option like multi-quantum well. So you can model multi-quantum well with the charge. So it means that many challenges that exist in the real world, like designing a laser modulator, you can use a multi-quantum well uh, tools from the Ansys that solve the Schrodinger equation, calculate the spontaneous and stimulated emission, support a different component, different quantum wells. So it's great. So how it works? So uh, actually, the output, the charge solve the drift diffusion equations. The output of charge go to the, I mean, now it's coupled, like multi-quantum well and charge is coupled together and solve self-consistently together. And then the output of this module goes to the optical solver, so FDDT and mode, and yeah, it's a great ecosystem. For instance, for um, PN depletion phase shifter, uh, we have a charge, Ansys charge here. By this chart, we can create a distributed profile. I will show you, and then you can the output of this part goes to the numerical mode, and then we can go to the numerical interconnect to simulate the circuits. So how it works. So like this one, you can see here. This is one example that I want to show you. By changing the voltage, we can see that our depletion layer in the phase shifter is changes. So let me go to the show an example in this case also. This one is different because I want to show you a numerical multiphysics. So this is the schematic of numerical multiphysics. So regarding the material, you can have a different material. In material, you can model a heat and optical property, and it was good. For instance, imagine that in a silicon case, you see here we have an electronic property, you know, DC permittivity, work function, and effective mass. You see here in the effective mass, we can see a different, dependent of temperature. So it's good. It means that you can model the heat, charge, and multi-quantum well in your simulation. And so this is a different recombination, shotcrete hole, Auger, and K dot P thermal. And in the thermal, you can see different parameter and you can visualize your structure. So this is the material part. But regarding to geometry, the same geometry that I showed in my PowerPoint, you can see that this is n++, this is n. We can add some doping. This is our waveguide, and here is our cathode. Here is an anode. So you can add your impurity as you wish. And for instance, let me show the charge monitor how it works. So for instance, here I change the voltage. Look, when I change the voltage, you can see the depletion layer changes. So this one can be imported to the numerical actually mode and then extracted to the numerical interconnect. So this is a numerical interconnect model. For instance, for this case, you can see here, this is a simple model. This is a simple model that is a modulator, act as a modulator. We put a designed, our design phase shifter here in the top arm and the bottom arm, and we put injected DC electricity to the phase modulator, and we have a two waveguide and different lengths, 5 millimeter and 5.1 millimeter, and these are war branch, and we want to see what's going on to the structure, like for instance, optical network analyzer. I click on optical network analyzer and I see the transmission. And then we can see that this is our transmission. And if I change this is our transmission. We can see different wavelengths, what's going on in the modulation case. Or here, if I put the line, you can see, I want to show how the modulator acts. For instance, I change the voltage. Look, when I change the voltage, we can see the place of peak changes. For this reason, we can modulate the light. So as we can see in this picture. Also, there are other options like because my time is limited, so to calculate the electro absorption modulator, you can see this kind of structure and model it, and this is the whole ecosystem, that how it works: Ansys mode, Ansys charge, Ansys interconnect. These are work together to model the electro absorption modulator. So we can model a laser. We can model a laser, and like this laser device structure, like this one, and we can use a MQW gain solver. Actually, MQW or multi-quantum well gain solver solve the gain, spontaneous emission, and simulated emission. As you can see here, this is a band structure, and this is our gain, and this is our band structure based on wave function. So these are some example for regarding to the spontaneous emission versus frequency for different parameters, different temperature. And this is a multi-quantum well edge emitter laser is some example of these items. Ansys mode, the output of Ansys mode goes to the Ansys multi-quantum well and then numerical interconnect.